I would like to share my screen right now. This will be full screen. The slideshow. So in today's presentation for my final project of topics in wind engineering, the topic of this project is called Methodologies to Mitigate Wind-Induced Vibration of Tall Buildings. For the outline of today's presentation, we will have an introduction of the topic. Then we will explain the types of auxiliary damping devices, then the passive approach for this, and conclusions. For the introduction, we have that the demand for more construction due to an increase in businesses, residential areas, and better construction techniques has resulted in more high or tall buildings around the world. As buildings grow higher and materials get redefined and perfected, resulting in lighter and flexible buildings, makes these new high buildings susceptible to large amplitude wind-induced vibrations. Wind causes movement in tall buildings, and the response of occupants to this motion is becoming an increasing concern. Structural engineers need to guarantee that the resulting vibrations from wind are minimal and acceptable to both residents and property owners. As we can see from this chart, we have several pictures in which we can depict the instability of buildings under wind-induced vibrations. So here we have the wind speed profile, and we can see how as we increase in height, your wind speed profile increases as well, while the turbulence decreases. So when we have the tall building motion, we can see on this picture right here, this can affect the building by moving it sideways, thus causing occupant discomfort. In this picture, we have actually mitigation approaches that are used for wind-induced vibrations. From this flowchart, we can see that there's two mitigation approaches, one called the active approach and one called the passive approach. The active approach would be a more interesting approach due to the usage of damping devices. These damping devices generate control force by either inertia effect, they generate aerodynamic control force, or they change the stiffness to avoid resonance. They can also add energy to dissipate the materials and increasing the damping ratio, and they can increase the damping level. For the passive control design, we have two approaches or two ways of solving wind-induced vibrations. This could be done by structural design or aerodynamic design. So as we can see here, by the structural design, you can increase the stiffness or natural frequency or increase the mass. Or by cross-section modifications, you can have things like chamfer corners, rounded corners, triangle corners, recessed corners, or slotted corners. Or shape modifications to the building. You can taper the building, twist the building. You can have setbacks, openings, or spoilers. So as we can see, we have many types of auxiliary damping devices. We can have a steel damper, a steel joint damper, lead damper, friction damper, viscoelastic, viscous oil dampers, tuned mass dampers, tuned liquid dampers, active mass, hybrid mass dampers, active gyrostabilizer, and active variable stiffness. We have some definitions for these damping devices. As defined by Zhang, a steel damper is one kind of energy dissipation device in structured passive control. Due to its simple structure, a clear conception, reliable performance, and easy implementation, scholars around the world have researched the effectiveness of this damper. can also have a steel joint damper, and the usage of this damper brings many advantages because of convenient manufacture, a simple structure, low cost, convenient replacement, and it is suitable for the main beam of fabricated reinforced concrete structures. And we also have viscoelastic dampers, and it is a common type of passive control device to reduce structural vibrations. And its performance is usually dominated by vulcanized viscoelastic materials. Finally, a viscous damper, it consists of stainless steel piston, a steel cylinder divided into two chambers by the piston head, compressible hydraulic fluid, and accumulator for smooth fluid circulation. And it works on the principle of dissipation of energy due to fluid flow. And finally, we have the other kind of passive approach. This is another approach used to reduce wind-induced vibration in tall buildings. And the definition is that passive control typically refers to damping systems that do not require sensors or actuators with external power sources to dissipate unwanted vibrations. The inherent mechanical damping primarily arises from material properties, making it challenging for structural designers to effectively manipulate this factor. Supplementary dampers can be employed to achieve the necessary overall damping for suppressing wind-induced vibrations. And it's important to recognize that the building's acceleration is inversely proportional to the square root of the damping ratio of the structure. These dampers are categorized into two groups based on their energy dissipation and system requirements, known as indirect energy dissipation, or IED, and direct energy dissipation. So in conclusion, there's two types of approaches to reduce the wind-induced vibrations of tall buildings. We have an active approach, and as you can see again, we have several types, right? And they provide control force by inertia effect. They generate aerodynamic control force, and they change the stiffness to avoid resonance. We have a steel damper, steel joint damper, lead damper, and many others. And for a passive approach, you can either change the structural design or aerodynamic design, in which you can increase the stiffness or natural frequency or increase the mass. Or you can do cross-section modification, as we already mentioned, rounded corners, triangle corners, recessed corners, or shape modification, tapering the building, twisting the building, setbacks, openings, or spoilers. And this will be my presentation for today. And hope you guys have a great time. And if you have any questions, you can email me too. Thank you.